The last topic we want to look at in chapter 17 is another application of electrochemistry called electrolysis. So electrolysis is when we start dealing with electrochemical cells from the looking at applying them to non-spontaneous processes. And so when we think about using cells, we get a spontaneous chemical reaction, and that outputs a potential. But what we can think is taking the same idea, having an anode, having a cathode, having them separated by, a wire. But now, instead of allowing electrons to passively flow, we're going to attach our cell to, say, a battery, which is another electrochemical cell or just another power source that pushes potential to cause a chemical reaction to occur. So that would be, this idea of I'm going to take, say, sodium plus, Cl minus, and I'm going to turn them into Na and Cl2. And that would have we can use standard potentials. We can think of what would this be. It would have a negative potential of 4.1 volts. What that means is if I have these reactants, namely sodium and chloride ions, and I apply 4.1 volts of potential, this reaction starts to happen. It is non-spontaneous in the sense that this reaction won't just happen on its own, but if I make it happen, it will. And so, the formation of NaCl is spontaneous. The delta G is very negative. So this would just happen on its own. This is how much free energy you could get out of the process. If we reverse the reaction, that has to be a non-spontaneous process. Delta G is positive 791 kilojoules per mole. What that means with the positive, we know positive energies are going into the system. In this case, that is how much energy has to go in as work to cause this reaction to occur. So it's not just that I would heat it up, but I am explicitly putting in this energy as work, namely flowing electrons in or driving potential, right? I'm applying a potential to this to make it occur, to make this chemistry occur. And this is a really valuable aspect of electrochemical processes, that we can make non-spontaneous reactions happen by putting in potential, by applying some sort of potential. So that's the spontaneous potential that would come out. This is the potential that has to go in to make the non-spontaneous reaction occur. So electrolysis, the main way that we use it actually industrially or in kind of in society is to break apart compounds into the elements. So electro means using electricity. Lysis means cut. So we are basically cutting apart or breaking apart compounds into their components. A really common application is in terms of mineral refining. So when you dig or mine, say for like aluminum, you actually would dig aluminum oxide out of the ground, Al2O3. What you do is then you apply some potential and you can get pure aluminum out of it, and then say leftover oxygen. So this is, you just take the oxide out of the ground. Oxides are a pretty common way that we find metal atoms in nature. You dig that out of the ground, you put it into, say, your power, and you just refine it that way. And so this is, for example, in Iceland, which is a major producer of aluminum. They dig the aluminum oxide out of the ground. They then have multiple, you will note, dams that are running as hydroelectric power plants. From a glacier, basically water coming out of the glacier. They take that, run it to a power plant. This power plant is only used for refining aluminum. So that is all. They just take an entire power plant, multiple hydroelectric dams coming from water from the glacier, and use that just to refine aluminum. And so you just use a ton of energy as electricity or of applying potential in order to get this to occur. So there's two ways you can do electrolysis. You can either do molten or aqueous electrolysis. So we'll start with molten. It is the more difficult to do in real life, but easier conceptually. In a molten sample, you basically are electrolyzing a liquid. So for example, if you want to do, for example, sodium chloride, you would say melt your sodium chloride. So this right here is molten NaCl. That means it's liquid. So this is very, very hot. You have melted your sodium chloride, and then you just basically put your electrodes into there and you react it. You are going to use inert electrodes here. If you remember, we're trying to run this in the non-spontaneous direction. Whenever you're doing electrolysis, you're going to use inert electrodes, because if you used an active electrode, like say sodium here, you would allow the reaction to start occurring in the spontaneous direction, right? You'd be putting in reactants together and they would start reacting. That would be a problem. So you use inert electrodes. Platinum's pretty common, gold, those sorts of things that really don't want to react, because again, you're applying huge potentials to this. You really don't want to get any sort of chemistry going. So say we're going to do some molten electrolysis of calcium fluoride. We want to think, what are we going to produce at the anode? What are we going to produce at the cathode? We know our reactant is calcium fluoride, and because it's molten, that means we are dealing with pure calcium fluoride, just have melted liquid calcium fluoride. It's very, very nasty, but let's see. So cathode is reduction. It's the same rules that we've learned before, red cat. So cathode is always going to be where reduction occurs. Reduction is the gain of electrons. Same rules still apply. So if we have calcium and we have fluoride ions, which ones can gain electrons? Well, the cathode is what can gain, the cations, sorry, are what can gain electrons. So you could have the calcium 2+ gain 2 electrons to become just pure calcium. For the anode, that would still be oxidation. Oxidation is loss of electrons. And so the anions are what can actually lose electrons to become just the neutral element. So in electrolysis, the cations react at the cathode. That's where the name comes from. And anions react at the anode. That's where the name comes from. So you get this sort of consistency that the anions are reacting at the anode, the cations are reacting at the cathode. And in electrolysis, you basically take those anions and cations, that's your starting point, is the ions, and you just produce element and element, whatever the kind of preferred element form is for that particular element. And so the overall reaction would be just the compound becoming the element. So that's kind of our standard idea of what electrolysis is. We use electrolysis to cause this to occur. Participation 1114, question 2. You are going to perform molten electrolysis of KBr in order to isolate bromine. A, which electrode will the bromine form at? And B, what will form at the other electrode? This is the second question on participation 1114, due Friday, November 14th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, you are going to perform molten electrolysis of potassium bromide in order to isolate bromine. A, which electrode will the bromine form at? And B, what will form at the other electrode? Outside of molten electrolysis, we can also do aqueous electrolysis, in which case we would say dissolve, say, our salt or whatever into water and then apply the potential. So this is more common because you don't have to, say, melt a salt. You're not working at, say, thousands degrees Kelvin. But you have an issue because water is a compound. And if you just apply potential to water, you can get electrolysis of the water. If you apply potential to water, you can take your compound water and break it apart into oxygen and hydrogen, the elements. And so at the anode, that would be a loss of electrons still. Anode is going to be anox, oxidation, so you're going to lose these electrons. And so you produce oxygen at the anode, and at the cathode, that's the gain of electrons, you produce hydrogen. And so you do produce these. You have these kind of processes where you can take your water and turn it into oxygen and hydrogen collectively, and then you do get this, overall creation of hydrogen and oxygen elements that then, bubble out or whatever, and you decompose the water. So if you're going to try to do electrolysis of a salt dissolved into water, we need to think about how do those kind of reactions interact with each other. So when you start to do this, say at your anode, there are two possible processes. Either the chlorides could be oxidized or the water can be oxidized. At the cathode, it's going to be reduction. Is it the sodium that's reduced or is it water that's reduced? And basically the choice is it will always be the most positive potential that happens, because that would correspond to the most spontaneous process. if you apply a big enough potential, theoretically, you could make more things happen, but generally it's always going to be the path of least resistance. So what has the lowest potential would be the most positive. You'll note all of these numbers are negative. None of these reactions want to happen, but you can see like this reaction at negative 2.7 volts really doesn't want to happen, whereas the -1 is easier to make occur. So even though you're trying theoretically to do electrolysis of NaCl, because it's aqueous, you actually don't produce sodium and chlorine. You would produce chlorine, yes, but hydrogen instead of the sodium. You don't make sodium out of it. That was just going to stay. This reaction, this top reaction, just isn't going to happen. This isn't necessarily always a bad thing. This is just something that will happen if you apply potential to sodium chloride. So one of the main places where we get sodium chloride solution is the ocean. So how we actually do this, you take your aqueous sodium chloride solution and you just apply a potential to it. And this is the overall chemistry that would happen. Your products are sodium hydroxide, hydrogen gas, and chlorine gas. And so this happens very close. The main place where this occurs in the United States is the upper Texas coast, because we have ready access to salt water out of the Gulf. And then you also are just applying a lot of potential. So you have plants down in Freeport. There's a big one where you have a liquid natural gas refinery. So you take the natural gas, they basically take all of it and they burn it to produce electrical potential. And then they just put that into seawater. And then you basically get your products from it are your gas, hydrogen, so you can produce hydrogen, useful chemical, you produce chlorine, useful chemical, and you produce aqueous sodium hydroxide, another useful chemical that a lot of these have some major industrial uses. So yes, you don't get pure sodium, but that's okay. You can get other useful things. And so the upper Texas coast is one of the main places in the country where this is performed. That's why chlorine primarily comes from this area as a chemical that we use in a lot of other things throughout this area to do refining and plastics manufacturing and stuff like that. But hydrogen, aqueous sodium hydroxide, it's all just about applying potential. You note it's 459 kilojoules per mole that has to go in, the E cell is negative 2.38. So you have to apply 2.38 volts. It's a lot of energy that has to go in. It's a lot of energy. So basically you're running like a power plant in and of itself just to provide the electricity to do this. Okay, we did have a participation question in this video. Only one more video left on this set. See you there.